Imagine a star, billions of years old, a colossal furnace that has burned brightly for eons. Now picture its entire magnificent existence coming to a crashing halt in just 10 minutes. That's what we're exploring today, the final frantic moments before a star goes supernova. This isn't just a slow fade to black. It's the most violent, explosive event in the universe, and we're going to count it down minute by minute. Let's set the stage. We're talking about a massive star, at least 8 times heavier than our own sun. For millions of years, it's been in a delicate cosmic balancing act, the immense force of gravity trying to crush the star into a tiny point is perfectly matched by the outward pressure from nuclear fusion in its core. It starts by fusing hydrogen into helium, then helium into carbon, and so on, creating heavier and heavier elements in a series of nested shells like a cosmic onion. But this process has a limit. The star keeps fusing elements until it creates iron, and iron is a dead end. Fusing iron doesn't release energy, it consumes it. Suddenly, the outward pressure that held the star up for millions of years vanishes. The delicate balance is shattered. Gravity wins. And our 10-minute countdown begins. 10 minutes to 0. The iron core, about the size of our Earth, but with the mass of our Sun, is no longer producing energy. The outer layers of the star, weighing trillions upon trillions of tons, are now in freefall, collapsing inward under their own immense gravity. The speed is staggering, reaching up to a quarter of the speed of light. Imagine the entire mass of our Sun crashing down onto an Earth-sized object in a matter of minutes. 9 minutes to 0. As the core collapses, the density and temperature skyrocket to unimaginable levels. We're talking billions of degrees. It's so hot and dense that atomic nuclei are literally squeezed together. Protons and electrons are forced to merge, creating a sea of neutrons. This process, called neutronization, releases a flood of elusive particles called neutrinos. These neutrinos are key. They'll play a huge role in what happens next, but for now, they are trapped within the ultra-dense collapsing core. 8 minutes to 0. The collapse continues. The core is shrinking at a terrifying rate. The outer layers are still plummeting inwards, completely unaware of the cataclysm unfolding at the center. For an observer on a hypothetical planet orbiting this star, everything would still look normal. The star would be shining as brightly as ever. The light from the core's collapse hasn't had time to reach the surface yet. It's the calm before the storm, a deceptive silence before the universe's loudest scream. 7 minutes to 0. The core has now been crushed down to an object only a few dozen kilometers across, about the size of a city. But its density is beyond comprehension. A single teaspoon of this material would weigh more than all of humanity combined. It has become what we call a protoneutron star. It's so dense that it can't be compressed any further. It's like hitting a wall made of the universe's strongest material. The inward collapse is about to come to a very, very abrupt stop. 6 minutes to 0. The moment of impact. The infalling material, still traveling at a fraction of the speed of light, smashes into the surface of this newly formed, incredibly rigid neutron core. The result is a shockwave of epic proportions. The material doesn't just stop, it bounces. This is the core bounce. An unbelievably powerful shockwave is born, and it starts to travel outwards, pushing against the remaining tons of material that are still falling inward. 5 minutes to 0. The shockwave is fighting a losing battle. Think of it like trying to swim against a powerful waterfall. The sheer weight and momentum of the infalling outer layers are too much. The shockwave stalls, losing its energy just a few hundred kilometers from the core. It looks like the explosion might fizzle out. The star is on the brink of collapsing directly into a black hole without the glorious explosion we call a supernova. But remember those neutrinos we mentioned earlier? Their moment has come. 4 minutes to 0. The core is still incredibly hot, and it's releasing an insane number of neutrinos. For a few brief seconds, This dying star's core outshines all the other stars in the entire visible universe, but in neutrinos, not light. These neutrinos are pouring out of the core, and as they travel, they slam into the material behind the stalled shockwave. 3 minutes to 0. The neutrino bombardment is relentless. While a single neutrino barely interacts with anything, the sheer number of them here is what matters. Trillions upon trillions of them deposit a tiny fraction of their energy into the plasma behind the shockwave. It's like a billion tiny pushes, all happening at once. This slow, steady transfer of energy begins to reheat and re-energize the stalled shockwave. 2 minutes to 0. The tide is turning. The energy deposited by the neutrinos has revived the shockwave. It's no longer stalled. It's pushing outwards again, and this time with renewed and unstoppable force. It's now a runaway reaction. The shockwave gains momentum, tearing through the star's remaining layers like a cosmic tsunami. The star's fate is sealed. It will explode. 1 minute to 0. The revived shockwave is now rocketing outwards through the star's onion-like layers of silicon, oxygen, carbon, and helium. As it plows through these layers, it heats them to billions of degrees, triggering a final furious wave of nuclear fusion. This is called explosive nucleosynthesis. And it's where most of the heavy elements in the universe, like gold, silver, and platinum, are created. The atoms that make up you, me, and the world around us were forged in a moment just like this. The final 10 seconds. The shockwave is racing towards the surface. 9, 8, 7. It tears through the star's hydrogen envelope, the outermost layer. 6, 5, 4. The surface of the star begins to bulge, glowing with an unholy intensity. 3, 2, 1, 0. The shockwave bursts through the star's surface. This is the moment of shock breakout. For the first time, the cataclysm inside is visible to the outside universe. An immense flash of high-energy light, mostly X-rays and gamma rays, erupts into space. The star instantly becomes billions of times brighter than it was just a moment before. In the hours and days that follow, the expanding shell of stellar debris, now superheated and glowing, will create the spectacular light show we recognize as a supernova. It will outshine its entire galaxy for weeks, a final brilliant testament to the life of a massive star. What's left behind is a rapidly expanding cloud of gas and dust seeded with the heavy elements needed for new stars and new planets. And at the very center, that tiny super-dense neutron star, a silent monument to the 10 most violent minutes in the universe. Thanks for joining this countdown to cosmic catastrophe. If you find the universe as fascinating as I do, make sure to like, subscribe, and hit that notification bell for more deep dives into the cosmos. See you next time.